So you guys, all right, go for it.
Welcome, welcome everyone. Welcome back, I should say. Welcome back. And we want to welcome Momchil to this is his 4th visit with us. So he's a long timer with the club. Thank you so much. I want to just say a little bit before you start. And we're so Momchil grew up in Bulgaria. How exciting. And came to the US to study physics at MIT. He's currently working, I'll say that, and then he can correct me, on his doctorate in solar physics at the University of Colorado Boulder. Momchil's studies are about the solar atmosphere and why it is so much hotter than expected. And he uses data from the biggest solar telescopes to do this. And this is so exciting. We're so excited to have you. And I'm going to pass you the mic. Welcome, welcome.
Thank you so much for the kind introduction. I really appreciate it. I'm just going to try to share my screen. Okay. Yes. Can you see my screen in presentation mode? Not in.
Yes, presentation.
Yes.
Perfect. Thank you. Well, thank you so much for the kind introduction. I'm really happy to be back. Since my last visit, I graduated from school, so I'm done. I'm no longer a student anymore. I work as a scientist in the High Altitude Observatory, which is part of the National Center for Atmospheric Research. It's a national center for studying the atmosphere of Earth and in general the whole planet as a complete system. So we study everything from how like the small scale, like the weather works on like very small scales, all the way to climate, and how like the climate on Earth is being changed by the sun, and that's how where I come in. And today I Adrienne requested that I rerun this the previous presentation I did for the people who missed it. And I also included a few more new slides with pretty exciting updates about the findings of the James Webb Space Telescope. So without further ado, I'm going to start going through the presentation that we covered the most ground. And then I would love to hear your thoughts and questions. And if you have a question throughout my talk, please feel free to unmute yourself and ask me right away. I'm more than happy to keep this as more of a dialogue than just me bumbling for like half an hour. So yes, okay. So, oops. Okay, perfect. So as many of you know, or you don't know, that's fine. Astrophysics is the science of studying the objects that are outside of our planet Earth. So astrophysics is the science about studying galaxies and stars and black holes and planets outside of our solar system, or the so-called exoplanets. And in order to study all these objects, we have very many different methods. And in particular, today I'm going to be talking about how to study them by looking at the light that these objects are emitting. So a quick introduction, there's a few different types of light. Our eyes can see the so-called visible light because we can see it. That's why it's called visible, and it's shown down here as the rainbow. However, there are many other different types of light out there. There's light that's more powerful. You can think it as more powerful, more damaging. That's on the other side of the blue color, the so-called ultraviolet. And even if you go like to more and more energetic types of light, you go into X-rays, which are being used to take X-rays of your body when you go to the doctor, or gamma rays, which are being emitted during certain nuclear reactions and other physical phenomena. On the other side of the spectrum, or like on the other side of the types of light, we have on the side of the red color, we have the so-called infrared, or like that's the type of light that very hot objects emit. And then on the other side, they're like microwaves and radio waves. So astrophysicists until now mostly used light to study objects. Today, I'm not going to be talking about gravitational waves. I can give a talk about it some other time, but we're not going to talk about this very exciting avenue of studying celestial objects. So in order to be able to study all different types of light, we have different observatories. And why we do that is because different types of light, they see different temperatures. So if you have an object that's like very, very hot, you're going to see it in X-rays. Or if it's something that's very cold, you're going to see it in microwaves, or like basically the same type of emission that your microwaves produces while you're heating up your dinner or something. So in order to cover all these different types of light, we have many different observatories. And NASA had this, this initiative to have telescopes in space to observe all of them at the same time in the late 80s and beginning of 90s, which extended into the 2000s as well. So we have the Compton, where did my cursor went? Oh, can you see my cursor disappeared. Either way, it's not as important. The important thing is, like, in astrophysics, we want to observe the most different types of light at the same time, because this gives us the most information. And over here, like all these blobs next to the telescopes they're shown are actually how our Milky Way looks like in the different colors. The leftmost ones are like gamma rays and X-rays, and they look very different from what we see on the right side of the screen, which is like infrared, visible, and millimeter. And by combining all this different knowledge, we can learn many different things about different celestial objects. So with time, actually, we acquired more and more observatories orbiting around Earth, which study together different celestial objects. And today I'm going to be talking about most probably the most powerful one out there, the James Webb Space Telescope. And that's why my talk is called like that. The James Webb Space Telescope was recently launched, and it's the biggest telescope in orbit ever sent in space. It's huge, and because it's so big, it actually can see significantly farther and deeper than previous telescopes. So, for example, this is not just due to its size, but the size helps. It's also like the more powerful instrumentation. But if we compare it to like the previous most powerful space telescope, Hubble, since the James Webb was built in a particular way, it can see way farther. And when you're looking into the night sky, if you're looking farther away, this means you're also looking more deeper into the past. Because looking farther away, you're seeing light that has taken a longer time to travel towards us. So it's a bit like a time machine. The farther away you look with these big telescopes, you're actually seeing light that's been created by these celestial objects billions of years ago. So the James Webb Space Telescope is basically the best time machine that we have out there in orbit. It's pretty crazy, but yeah, it's pretty insane. And in order to show it in perspective, the James Webb, like a model of the James Webb is shown here with a major part of the team around it. And you can see it's a massive facility. And that thing was sent in space, which I'm going to show you in a minute how it's done. It's pretty insane. But also something to keep in mind is that these big projects, they require really, really big teams that work together very hard to make them. And these, in order to make these teams, there are people from many different backgrounds and expertise that work together. So they're not achievements of a singular person working behind a telescope, even though the telescope carries the name of a certain NASA director from 50 years ago. This telescope was the fruit of the hard labor of like hundreds, if not thousands, of people working on it for like 30 years. And just for scale, how big the mirror is, like this golden plated mirror shown next to people. The mirror is like 6.5 meters tall, which is 21 feet. I'm not used to using imperial units, so every time it takes me a lot of effort to go back to feet. So like it's 20 feet, and it's pretty big compared to a regular human being. And now you're going to ask, okay, like this thing is huge. How did they fit it on a rocket? And actually, this is a short video from the launch. It was a very exciting moment, and it was also very stressful because that's a few $1 billion adventure. And if this thing exploded, it was going to be lost. So everything was very nervous. It was launched in French Guiana. That's why the person is speaking in French. And yeah, you can see it's on a really big rocket.
James Webb begins a voyage back to the birth of the universe.
Yep, that was really exciting to watch last year.
Punching a hole through the clouds.
But the coolest thing, I think, is that actually putting the telescope in that rocket, it had to be folded pretty much like a small puzzle. Like if you've ever played with one of those small puzzles that you have to figure out how to take apart, that have a bunch of rings and balls and like strings attached. That's pretty much how this telescope had to be folded to be able to fit it on the biggest rocket we have, since it's so big. And over here, there's a schematic how it was fitted in. And this is a short movie, I hope works. Yeah, that they're showing how the telescope is deploying in space. And the pretty crazy thing is that there was nobody to safeguard anything happening. So it had to be like 100% certain that it was going to work out by itself. So this was the most complicated, or at least one of the most complicated up to this point, folded spacecraft was ever sent in orbit. And you can see how, for example, the main mirror is like folded into a few different segments. And just to give you a perspective, this mirror has to be precise down to a few hundred atoms spacing in order for the telescope to operate precisely. So like everything had to be extremely precisely done, and this was like a major feat of engineering that was happening right there. So what you're seeing right now actually is like the telescope was folded, and then what they are actually deploying right now is like the so-called sun shield, because the actual telescope has to be cooled to a few hundred, 180 degrees below freezing, in order to keep it cold enough that its detectors can actually see the light coming from these very distant objects. And all of this went brilliantly. The tests, this is like a sharpness check, or like how well the telescope is seeing, went very well. It was like, you can see all the stars are extremely sharp like points, which meant like everything went perfectly. And if you go, NASA has a website, you can see, and you can go on this link. I'm going to share these slides with you later. You can go and check how's the telescope is doing. And actually it's doing pretty well. Everything is going nominally, which means that everything is going great. And as you can see here, everything is cooled down to like very low temperatures in order to be able to detect this very faint signals from faraway objects. And just a few, let's say, engineering details about the telescope is that actually it's it actually took 40 million person hours for it to be built, which is insane. It was like many years of like hundreds of not thousands of people's lives was like was the child of this. And in order to make this telescope work, actually the sun shield of it is so good, as if you're applying like SPF 1,000,000 on your skin. It's like it's so well shielded from the sun, and it's extremely sensitive. My favorite fun fact that's pointed here is that actually, if you point this telescope to the moon, you should be able to see the heat signature of a bumblebee just going around, which is really far away, and to see just a singular, like the heat coming from a singular bumblebee, it's like so precise. So getting back to it, we will be able to study all of these things, like all of these celestial objects, in like great detail using it, because it's working great. And I'm gonna try to start going through these through the different science uses of this telescope in kind of an order of increase of the size of the object. So I'm gonna start with the smallest things. I'm gonna start with how the telescope is actually, oops, is this gonna work? Oops. Oh, my video is not working. Oh, okay, never mind. So the telescope is gonna be actually used to look at stars around other planets. And previous observations from Hubble have shown like some of those, but we expect with the James Webb Space Telescope to be able to see way more than that. And over here, I hope this video works. Yeah, and especially something very useful would be that we'll be able to look for signatures of life in these planets that we're going to be studying. And how this is done is, I think this is a very cool video that's illustrating the process. So once you have a planet with an atmosphere, when you have a planet with an atmosphere, once this planet passes in front of the host star, it makes this dip in the brightness that we can see. But the more interesting thing is, like, when you have incoming light from the star, the light that passes through the atmosphere actually has signatures of the composition of it. So we can see if there's oxygen or other signatures of life. So basically, the telescope is going to be looking at the light coming from the atmosphere of these small planets orbiting their host stars, and it's going to look for these signatures that are going to be shown right here. And in order to look for these signatures, we break down the light into different colors, or like the so-called spectrum. And in the spectrum, when you have molecules, they talk a little bit about what I talked a little bit before about the different types of light. Different parts of the spectrum basically get bit away by the molecules in the atmosphere. Yeah, as they're showing here, you can figure out what's the absorbed light. So for example, if you have carbon monoxide, which we think, or water, which we think is actually a signature of life, if we can detect this in this way, we can start actually thinking, oh, there might be actually life there, which is kind of pretty cool, because this is like, we're going to be actually starting to try to answer the question, is there actually other life in the universe, which is I think one of the big goals of astrophysics nowadays. Yeah. And oops. Oh, yeah. But actually, we don't need to look for life so far away. We can actually look for life closer to home. And in particular, there's so many moons in the solar system. Almost every other planet, except for Venus and Mercury, have actually, I think beside those two, every other planet has a significant and big moon orbiting around them. And all these moons have very different conditions on them. So by using very similar measurements with the James Webb, we'll be able to look at these like similar molecules that we think are signatures or like signs of life. For example, Europa is a very big moon of Jupiter, and we believe that there is an ocean underneath its crust of ice. And sometimes they're like big geysers. It's a little bit like just like exactly like the geysers on Earth, but like way bigger. They erupt from them. And if we look at the actual chemical composition of them, we might start seeing these key signatures, so like these signs of life in those. And I just want to say that it's extremely hard thing to interpret these measurements, and just detecting that there's some sort of molecule that's being created by life on Earth doesn't mean that detecting it there means it's created by life there. So there's a lot more science to be done before we can say like, oh, we see this, hence there's life. I think there's a lot more very hard physics to be done. But these measurements are very unique and going to be extremely valuable for studying life. Also, the telescope is going to be studying the life of stars, which is a bit more esoteric, to put it mildly. But stars are actually super important for just being the building block of everything we see in the universe. So understanding how the life of the stars proceeds is very important. So over here, for example, I've shown two different pictures of where stars are born, the so-called stellar nurseries, or like these big nebulae of gas, where under its own gravity, these clouds of mostly hydrogen collapse and produce new stars. And on the right, I've shown the Ring Nebula, which is a remnant of a dying star. When a star is dying, it actually in some cases, the star actually expands its outer layers and creates these beautiful ring-shaped nebulae. So just quick comparison between what Hubble was able to see and what the James Webb can see. Over here, I've shown you one of those stellar nurseries where stars are born. And on the left is a Hubble image, and on the right is a James Webb image. And you can see just how much more detail there is in the right image compared to the left one. How many more stars, how much more detail in the clouds there are. And this is due to the larger size of the mirror of James Webb, but also the fact that it looks a little bit more towards the infrared, or you can think of it to the red part of the spectrum. And by looking a little bit more to the red part of the spectrum, you can see a bit deeper in these very opaque clouds of gas and dust. Hence, the James Webb can see a little bit better what's happening in there. Also, another comparison is the Ring Nebula, which is a very famous nebula, and we believe that it's a remnant of a dying star. And in the center of it, there's actually a neutron star. The neutron star is it's what's left over from the dying star. It's like very, very small, and it's rotating hundreds of times, if not even faster, around itself per second. So it's a pretty crazy object, and you can kind of see it over here. I think, okay, I might have lied. There might be just a white dwarf in this one. Sorry, I think I made a mistake. In this one, you actually have a white dwarf. Like the central bright star you're seeing in the center is the core of the star that's being left out. But on the left, you see an image with Hubble, and on the right, you see an image from James Webb. And you can see how much more detail and how much more small scale faint things you can see with the James Webb. And this is really going to help us understand better how these late stages of the star's life proceed. Also, we'll be able to study galaxies and how galaxies evolve, and how are actually galaxies being formed, which is another big problem, because it's kind of hard for us to create the distribution of galaxies we see throughout the atmosphere, throughout the universe. And actually, when you compare what Hubble sees with what the James Webb sees here on the left and right, you actually start seeing very, very way more structure and extremely more small scale, which is very important for building good models of galaxies. And also it provides us with more diagnostics of how the stars are distributed in the galaxies and so on. So you can see here on the left the old image and the new image, and just by comparing the two, you can it's pretty mind-blowing what you can see with the James Webb. But also, as I mentioned earlier, James Webb is going to be time machine in a very, very special way. Since the James Webb can see the light that's coming from the first stars, because it observes a little bit more to the red parts of the light spectrum, it can actually see really far away. So over here, we kind of have a schematic of how the universe evolved up to this point. So on the way out right is the Big Bang. That's when something happened. Like, I think this is the best way to describe what happened, but like something happened, and then the universe started as a very, very small and condensed place, which was extremely hot. Then it expanded and became kind of dark, because there were no stars, and these are the so-called dark ages. A little bit later, when it expanded and became a bit cooler, the first hydrogen atoms were formed, or so-called the first ionization. Then we started forming the first very bright stars. Well, at least we believe that the first very bright stars were formed. And around that time, there's a lot of unknowns about how really the universe evolved. And we hope with the James Webb to be able to probe this region, which is almost 13 billion years ago. It's like, you can think of it as either like being 13 billion light years away. And since it's so far away, the light that was emitted from there travels to us in 13 billion years. So that's what I mean by James Webb being a time machine, is because it seems so far back in the past. And by exploring this, we hope to learn a little bit more how the dark age, what happened before the dark ages, and how the Big Bang happened and all of this. So in order to do this, James Webb is actually going to be studying the first galaxies. And in order to do that, you got to look for a very long period of time. So for example, this image that I'm showing you here, it required Hubble to stare at this one particular very, very small patch of the sky. It's like way smaller than a nickel. If you put a nickel up on the sky and you look at it, this is like way smaller than that. They spent like a week looking at this place with Hubble just to get this image, and this image is extremely deep. You can see really, really far away. But comparing it with JWST, comparing like a similar image taken with JWST, like on the left is Hubble, on the right is JWST, you can start seeing way more detail. By I think JWST took a few hours, whereas Hubble required like a week to obtain this image. So JWST is way better for that, and we can see like so much more detail. And like, I don't know, if on the right you start looking at these very elongated structures, these are actually galaxies that are way back the front galaxy, like the galaxies in the foreground. But since the galaxies in the foreground are so heavy, they're actually bending the light and acting as an artificial telescope to be able to see those very bendy and like small pancake looking shapes. So, and these things are like very, very old. They're on the order of like 10 plus. They're like on, I think, between 8 and 10 billion years old. So this is a very, very old galaxies we can see. But actually, if you start looking at, actually, this is one of the coolest things that came out was that actually by looking at very, very deep exposure, so like basically the telescope was obtaining, was collecting light for a very long period of time. Because our eyes, just a side note, our eyes, you can think of them as collecting light for a very small fraction of a second. And that's how we make the images around us. Telescopes are really good because they can collect light, not for like a part of the second, but they can collect light for a very long time, like for days and weeks in a row of the same object. And that's how they see they see objects on the sky that are like way, way dimmer than what we can see with our bare eyes. And over here, I think the telescope looked for a very long period of time, like it collected for many hours light, and it saw like this like very small blimp that actually is formed at what was it, like 13? Yeah, this thing was like 13.3 billion years ago, which is pretty crazy. It might have been like one of the first. I don't know. I don't even know what this object is. I need to check, but it's most probably some sort of a remnant of a galactic nuclei or something. But yeah, like we can start seeing these objects really, really far back in the past, and trying to figure out what they are is extremely not trivial. It's like very complicated. So just to wrap it up, because I think I've been speaking for almost like a little bit, like around a half an hour, and I would love to open it for a discussion, is that the James Webb is out there starting to collect data, and a lot more very exciting discoveries are, I think, about to come. And be on the lookout for that. And I would love to take your questions now. Hope that not everybody's asleep.
I learned in one of my science classes, like the phrase "we're all made of stardust" is because like we're made of like similar elements that only like big high mass stars can create. Can you explain more about that?
Yeah, that's a very good point. So when we're made mostly out of water, which is hydrogen and oxygen, a lot of carbon, because all of the complicated molecules like proteins and proteins and fats and carbohydrates, they're all based, they're like the building blocks of our bodies. They're all based on very long links of carbon. So in order to make carbon, you need to have a star that can mend together hydrogen atoms, and by mending them, it creates helium. Then it takes like helium and maybe a hydrogen or something else, and it creates like even heavier, like lithium, beryllium, and heavier atoms. So in order to start from like what the universe was in the beginning, mostly hydrogen, in order to get to the point where we have actually carbon, what we're mostly made out of, you need a big star, like most probably something bigger than the sun, that can actually mend together atoms and make heavier ones. Like, for example, from hydrogen, it creates a bunch of ones that that end up being carbon or phosphorus or potassium and all the other things that we need to build our bodies. So we are in a way made out of stardust, because in the beginning of the universe, there was no carbon to make ourselves. There must have been a star that created all these elements that are in us. But even more interesting is that in order to start making precious metals and other very heavy, like lead and other heavy elements, you actually need very heavy stars either dying or coalescing and creating and making black holes and all this kind of stuff, which is kind of crazy to think that all of the given objects around us are actually created by stars. It was basically everything that's not hydrogen based is coming out of as a byproduct of a star. Yeah, I hope this answered the question.
Momchil, how far out can the telescope go based on its position where it is today?
Well, this telescope is actually kind of far away. It's about a million miles away from Earth. It's like they sent it in orbit really far away because they wanted it somewhere that's cold and that's like kind of far away from Earth, and also like kind of a little bit away from the sun, because the sun is too bright. Like this thing is measuring like really, really faint objects. So you need to keep it really dark. And that's why they kind of kept it away from Earth. They sent it really far away. But once it's there, it's the so-called Lagrange point. So this telescope is always going to be on the line that Earth and the sun makes. And if this is okay, let's say this is the sun, this is the Earth. The telescope is like on this side out here. I think the so-called second Lagrange point. So it's always trailing on the line between the sun and the Earth. And since it's there, it can actually look away from the sun and look at very faint objects. Because if the sun is somewhere around, it actually heats up the telescope and it's very disruptive for making its measurements.
Thank you.
Mm-hmm.
So are they pretty much mimicking what the Hubble has taken pictures of so far as a stare and compare? As you have?
Well, kind of. So a lot of the data that they're taking is in the form of spectra. Spectra are light decomposed in its constituent colors, basically the colors that make up the light. And those are not too exciting to show to the general public because they're basically, you can think of them as like squiggly lines. And those are kind of not as fun to watch. And that's why for public relation purposes, they took a lot of the cool images that Hubble took to be able to show to the general public. But to the scientists, actually, the most interesting things are coming out of these spectral observations, which are showing the different colors that create the light coming from these objects, because that's how we learn the most. Even though images are very important, nowadays we are taking a lot of spectra as well. But to answer your question to the point is that they did redo a lot of the famous Hubble observations just to prove that this telescope is way better. Yes. But also I think we learned a lot more from those because there's like so much more detail and more information in them.
Yeah, it was. I really liked the stellar nursery photo.
Yeah, it's pretty amazing. I didn't show you the full resolution, but it's somewhere on the internet, and it's like way higher resolution. Yeah, I see. Easy has a question.
Yeah, why was it decided that the mirrors needed to be hexagon shaped? Just to go together easily? Or?
I think so. Yes, I think that was part of the. That was part of the design, because I think it's easiest to like just get them together. And also, yes, I think this is the answer. Yes, because I think the easiest way to fold them together. Yeah.
And then gold, was there a reason they selected gold as an element to make them out of?
I think because it's just I think it's because they're looking into the infrared, which is a little bit more toward the a little bit more on the other side of the red part of the rainbow, the spectrum. So I think that was just the best coating that they can make, because it's, I think, a combination of beryllium and gold. I think it's not pure. Yeah, I think it's actually yeah, I think it's like the mirror itself is like beryllium based, and then there's just a coating of gold to protect it, because I think gold doesn't really react too much with air. So in a way, you're like protecting the mirror that's underneath. It's not like a pure gold. It was going to be too expensive to make it that way.
That's interesting. Thank you.
I think Mary had a question.
Is that
It's in the chat. Can you see it?
Yes. Oh, very good question. The question is, are the stars and planets actually the colors shown in photos? No. No. So the problem is that if you've ever played with a color filter, for example, you have a blue color filter and you put it in front of anything, everything looks blue. So, and that's because every object around us creates light, emits light in all colors. So how we perceive the color of the object depends on what type of light it emits, but also like how sensitive we are to different colors. Our eyes are really sensitive. They're good in seeing blue, but not too well. We're really good at seeing green and yellow, and that's because our eyes are very accustomed to the most light that's coming out of the sun. And the sun is actually, it's kind of surprising, but the actual color of the sun is green because it emits the most light in the green part of the spectrum. So our eyes are really sensitive to seeing like green and yellow things, not too much like the deep red. But our telescopes, they can kind of see almost every color. So just to present the colors of the different objects, we have to make choices, because we can't really translate what the telescope sees, because it sees different colors than our eyes. So everything that you're seeing as colors of different photos, unless it's like stated very clearly that they are adjusted to the color, to the sensitivity of our eyes, they're false colors. Like if you go to this object and you see it with your eyes, most probably it's not going to be these colors. It's just that you can think of it as an artistic impression on the coloring scheme. I hope that answered the question.
I think so. And I'm glad you asked that question, Mary, because I assumed that we were seeing those colors. So it's a good thing somebody brought that up.
Yeah, they're not those colors. Yeah.
Someone raised their hand, Izzy.
Yeah, another quick question. What made you decide to go into astrophysics, Momchil? Just curious.
Oh, that's a good question. I was always interested as a kid, and while making my career choices, I weighted in the positives versus the negatives, and I decided it's a fun profession. I mean, I was thinking like if I can get my hobby to be my professional endeavor as well, that would be pretty neat. And it turned out to be the case. It's been really interesting, because being a professional scientist is challenging, because for many reasons, including the funding situation is always a little bit precarious unless you're teaching, and then you can't do that much research. But on the other side, the positives are like that it's a very stimulating profession. You got to think hard about many things a lot of the time. And besides working with telescopes, you get to travel a fair amount to meet people and work together on projects, which is, I think I really like. And you also get to write a lot and publish a lot, which I get to enjoy. I'm getting to enjoy it more. But there's like a lot of different facets you have to do in the job, and it's very, at least for now, it's very free of bureaucracy and corporate endeavors, like dealing with people, which I really like. Yeah, so and it's a lot of math, which I also really like. So that's what made me choose this path. And the US is the place to be, really, because NASA has been supporting this kind of science for a long time, and it's enabling a lot of amazing science. Yeah. Huh. There's a question in the chat. Is the telescope not going to be blown away in space by the wind? So the outside of Earth, there's the so-called solar wind, which is a stream of particles that's moving from the sun outward, and it's pretty fast. It's going with speeds between like 200 and something miles up to almost 600 miles, if not even faster, depending if there's some sort of special event. So, but this wind, even though it's so fast, it's actually not very dense. So you can think of it as a gentle breeze. So the telescope is not going to be blown away by that. The big problem with this telescope is that is the gravity of the planets. Like once you start going into space outside of Earth's atmosphere, the dominant force is gravity. So like the pull from other massive planets, mostly Jupiter, actually. So as long as Jupiter doesn't mess up your orbit, like doesn't pull you away, you're pretty much safe. And this Lagrange point, the place where we send this telescope, is actually kind of a stable position. Like if you stay there, you're most probably gonna stay there for a while. So that's why we sent it there, because once we send it there, we don't need to use the engines on the telescope anymore to move it around. It just stays there, mostly. Oh, can you comment on? Okay, next question, which is way more technical, and I might not be able to answer it. Can you comment on stray light and how it was controlled with on JWST? Okay, so once you have a optical system like a telescope, and you have light that's coming, like once you start collecting the light into your detector, you're hoping that all of the light that's coming in is from the object you're studying, and it's not, and it's always collected in the same place. So to be completely honest, I don't work on James Webb telescope, so I'm not sure how they are controlling it. But as far as I understand, they need to do that very precisely for its coronagraphs looking for planets. And to be honest, I'm not sure. Yeah, I'm not part of the project, so I'm not sure. Okay, there's another question in the chat. Hubble's law says that the galaxies are moving closer or farther away from us, and we can calculate that using the Doppler shift equation. Have you ever calculated the speed distance of a galaxy before? What can we learn from this? Okay, great question. Myself, I studied the sun, so I haven't really done it for real. But so at some point in university, we had a homework about it. So what the Hubble law says is that because of the expansion of the universe, if you look at the galaxy that's kind of far away, it's going to move away because the universe is expanding. So the farther away the galaxy is, the faster away it's going to be going away. Like it's going to be just moving away from you. But so you can kind of think of the universe as a little bit of like a balloon that's expanding and like moving out. And the crazy thing something to think about is that if you're actually in another galaxy, you're going to see the same thing. You're going to see how all the galaxies are moving away, which is kind of incompatible with at first thought, like if you're actually it's another galaxy, because you again see everything moving away. So it's kind of mind-boggling deduction at the first moment. But using the Doppler shift equations, actually, if I can go back to my slides, can you still see
Yep.
my?
Yep.
Perfect. So actually, once we're once I was talking about these like very distant objects, the way we figured out they're so far away is by using Hubble's law. So people are still using that a lot to figure out how far away these objects are. And how they do that is actually by looking at light coming from that should be visible, and even like UV light that's moved all the way to the infrared. It's like so redshifted because of Hubble's law. And that's why this telescope is observing in the infrared, because we expect these really far away objects, their light to be shifted to the infrared because of the expansion of the universe in the Hubble's law. So this, like in a way, Hubble's law is being used all the time for these type of measurements, but it's really hard to apply it, because once you start looking at the spectral lines, these features, these colors that we kind of observe, they're actually really hard to identify. So it's an art. It's an art to use Hubble's law nowadays, because it's really hard. Yeah. Okay. The next question is: if we were able to deploy a telescope like the James Webb further out into our solar system, maybe past Jupiter, would it be possible to see into the Big Bang? Sadly, no, because this is not like on the universe scale. These distances are not very large. Like from here to Jupiter is like nothing compared to the scale of the universe. Like for example, from Earth to the sun is about 8 light minutes. It takes 8 minutes for the light to come from the sun to Earth. I think from the sun to Jupiter is something on the order of like 35-40 minutes, if I'm not wrong. I think maybe 35 minutes. So, and the distances I'm talking here about are billions of light years. This is like how far the light travels in a year compared to like from here to Jupiter being like 40 minutes. So like just moving that far away is really not going to change our vantage in the universe. We're still going to be far away. Yeah. But there's other ways to look into the Big Bang using telescopes that are actually looking at radiation, like at light coming from the actual pretty close to the Big Bang, but it's like so far away that it's moved past the infrared. It's like into the millimeter and radio. And those are the telescopes like on the South Pole or like in Australia and desert that are looking into those. And those are a bit better for that. Okay, so the follow-up to the question was, there's not much interference to our visibility between us to see outside our solar system. Absolutely correct, yes. There's not that much stuff. Like once you get above the atmosphere, we don't get a better vantage point than that. Yeah. Okay, next question. When you talk about gravity, do you mean that the gravity pull from the planet can have objects crash into a planet, like meteors? Kind of. Well, I was mostly saying that if you have something in orbit, and if you have another big planet like Jupiter going around, over the course of many orbits, you're actually going to have a small change in the initial orbit of the body. Like it's like a very small change. It's not really that body like falling like a meteor. But since the time scales, like how the times that we're talking about are like millions and billions of years, even a very small change in the orbit over millions of years leads to systematic effects, which actually affects how like comet orbits and stuff like that. So on our lifetime scales, things don't change too much, but on like very long time scales, things change a lot due to the gravity of other planets. Okay, next question. How well can we study atmospheres of exoplanets, or are the integration times too long? How long are the integration times typically? So that's a great question. So when you want to observe a spectrum coming out of the atmosphere of a star, you're limited by how long is the star passing by in front of the star. Usually, if you're doing like the transit spectroscopy, like when you have the star, you have the planet, and then you have your telescope over here. So that's pretty much limited by the amount of time that the star passes in front, and that could be from the order of minutes to hours. So you basically try to collect a light for like minutes to hours, and you kind of integrate for the whole time. And usually what we do nowadays, especially from the ground and also in space, is that we don't really open the shutter of our telescope for a whole hour, for example, we usually take a lot of images in quick succession. And in this way, we can sum them up and get a better image. And this was allowed by recent progress in the cameras that are being used. So the integration time is always going to be as long as possible is the answer. And it's really hard to do right now. So people are just trying to take as long as possible they can. So, and also with the James Webb, we're hoping to actually be able to actually put the star behind a small occulter. Like you can think of it as an artificial moon in a solar eclipse. When you have in a solar eclipse, the moon goes in front of the sun. You don't see the sun anymore. Something similar is being done with the James Webb, where they have like a small artificial moon that goes in front of the star, and you only get the light from the planet. But that light is very, very dim, and it's very hard to study. So in that case, I think they integrate as long as they can. But I don't think I've seen a solid result from that. But there might have been some recent ones. And to wrap up, I think we might be getting even better observations of that with the new generation of 30-meter telescopes on the ground, like telescopes that actually have mirrors like that are 30 meters. And even though they're on the ground, they're gonna collect like 20 times more light than the James Webb. So I think they might be even better for that. And that's again gonna be like many hours of integration to be able to answer that question, because like it's just a very, very hard problem to observe.
So you got the 30-meter telescope in Hawaii?
That's not. I don't think that's happening anymore.
Oh, really?
Yeah, because the locals were not very happy with it. So
really?
I think it's going to be somewhere else. Not sure where.
Okay.
Yeah, but there's going to be a 30-meter telescope on La Palma in the Tenerife. On the Canary Islands in Spain. That's where the Europeans are building theirs.
So we're going to take a field trip to their facility in Monrovia, California.
Oh, cool.
Yeah, we'll tell you about it.
That's really exciting. Okay. The next question, I have one more question. Will the telescope be disintegrated by the heat of a star? Good question. So when you're looking at the night sky, no, it's pretty like there's not enough light coming from that. But if you're studying the sun like I do, the telescopes we use are actually the biggest problem with building a solar telescope is like, what do you do with all the heat? Because if you've played with like a magnifying lens and you point to the sun, and at the point where the light is collected, you can burn things. Well, imagine that the small magnifying lens was not that small. It was like 4 meters or something. Then you actually have something that's way more powerful than the oven that you have at your house. Like it's 10 times more, most probably more powerful than what you have in your house. So what do you do with all this heat is the big problem. And actually it's been a very, it's an engineering feat to be able to deal with that much light. And yeah, so if you're building a solar telescope, that's always a problem. Because like, for example, the new telescope that just got commissioned on Hawaii, they burned something by mistake not a long time ago, because there was like a little bit of a glitch in the system. So it's actually a very dangerous thing, because like if there's a person in the wrong place in the telescope, they can actually get burned alive. So you got to be really careful operating these big solar telescopes. But nighttime telescope is fine. Like nighttime telescope, it's pretty mellow. Yeah. Okay. Being an astrophysicist, do you have time to do anything else? Or is it pretty demanding on your time? No, I think it's a pretty regular job. I just have a 9 to 5 work time, Monday to Friday. But sometimes when we're in, there are big projects that are due, sometimes we have to work a little bit more, but it's really not that bad. It's pretty regular. Yeah. We have 40-hour work weeks, like a lot of other occupations. Okay. Fun fact. It was an astrophysicist who first came up with the theory that it was a meteor that wiped out the dinosaurs. Oh, I didn't know that. That's a cool fact. Thanks for sharing that.
So did anybody send you any more personal chats? I don't see anything else here. So Momchil, thank you so much. Oh, wait a minute.
Oh, there's one more.
There's a couple of more. So I overspoke. Go ahead, guys. Go ahead and read those.
Oh, has it been, okay, the next question is, has it been considered to create ignition instrument or pulsed laser at astrophysics level? Can you elaborate on that? Because I think I can answer, but I just want to make sure, because ignition in terms of fusion, or yes, okay. So, well, we can't really do fusion right now because we kind of can do fusion right now, but in a not very self-sustained way. But there's been a lot of experiments that are being run to be able to figure out how atoms behave at these plasma conditions. Because when it's really hot and really dense, and atoms behave in a very different way than they behave in our regular labs. So in order to be able to calculate how stars are going to evolve, or like how black holes are going to look like, and all this kind of crazy stuff, you need to know how opaque are atoms in these crazy conditions. Also, kind of a coincidence, it's very important for nuclear weapons. That's why there's been like so much money spent on it. But it's very useful for astrophysics as well. So we're piggybacking on that. Yeah, getting back on it, there's been a lot of instruments that are, I think, in like Sandia National Lab and all these other crazy places, like the national labs. They've been doing a lot of experiments trying to measure at astrophysics conditions what are the properties of atoms, because that's the heart of the models we make about these like stars and galaxies and all this kind of stuff. So we've been using those, and at astrophysics level, I would answer like we've been trying to replicate the astrophysics conditions, like almost in perfect vacuum, for example, and stuff like that. But building something as big as a star, it's never going to happen, because we don't have, well, not never, I shouldn't say never, but yeah, yes, yeah. Well, if you mean like the target, the way of doing fusion with targets, that's like a very specific, that's one way of thinking about it. Let's put it that way. That's as far as I understand, that's like a very nuclear weapon centric way of studying fusion, because they use that to benchmark some other like weapons. But yeah, there are many ways to build like some sort of a plasma environments where we can study plasma physics. Yes, there's been a lot of, yeah. The answer is yes. There's been a lot of effort to have plasma astrophysics being done. Yeah. How do we become better at physics and math? Well, you pay attention in class. Not to be the most trivial, yeah. But I don't know, you pay attention in class and do your homework, and yeah, that's been yeah. And I don't know, try to, if you're interested in something, just try reading about it and try exploring it a bit more. I think that's how I've learned a lot of things while I was in high school. Just being curious about things, ask questions. Yeah. And yeah, if you feel free to contact me with any questions you have after this chat. I think I should have left my email somewhere, but Adriana, I think you have my
yes, I do.
email. So please share it with everybody. Yeah.
Yeah. And the people that are here from Eventbrite, I think it's a section where they say you can get in touch with me. It'll go straight to my email, and I can email Momchil, as we've been in contact with. I was scared at first, because when you said you graduated, I was like, okay, he doesn't even have the same address anymore. So I'm not able to find him, but I was able to, so don't go far. But we thank you so much. And he's on rotation all the time. Now you guys see why, right? Just a wealth of knowledge, and we appreciate you coming to spend your hour of your day with us again. We know you're busy. You were studying half the time, and we just watched him from, gosh, you were like maybe 2 years in only when you started?
Maybe, yes.
Yeah.
It was a long time ago.
A long time ago. So if you guys want to get in touch with Momchil, just let me know. And if you have any additional questions, feel free to ask them and he'll get back with you. Okay?
Thank you so much for hearing me. I really appreciate it.
Oh, thank you so much.